negative. Let's go to the fourth segment of the lecture of today. Let's look at the end of that. Actually, let me go back to chapter 3 of whose book to make another point to you. Okay. At the end of last lecture, we saw two sets of nonlinear differential equations based on the Lagrange-Euler representation of a two-linked robot. The rest of this chapter is the Newton-Euler treatment of the same problem. Let me go faster this way. Yeah, it's a Newton-Euler formulation. As it says here, in the previous section, the set of nonlinear second-order differential equation from Lagrange-Euler formulation was obtained, which described the dynamic behavior of a robot arm. The use of these equations to compute the nominal joint torques from the given joint position, velocity, and acceleration. So, in the Newton-Euler representation, this derivation is based on the Alembert principle and the set of mathematical equations that describe kinematic relation of the moving links of a robot arm with respect to the base coordinate system. In order to understand the Newton-Euler formulation, we need to review some concepts in moving and rotating coordinate system. So it is fairly complicated, but the idea is this, that every link of the robot from base here, the motion of individual links are separately represented with respect to the base. Then it integrates the whole thing. And the result is the same as before. For example, let's look at the simpler version of it. This is, of course, the Puma 560, a more general description of it. And here is the two-link version of it. Here you have a whole set of rotational matrices. And you come up with a set of equations called forward equations, and going through a whole bunch of calculations, which is really too much time consuming that I can do it for you. But nevertheless, look at the final result. Final result will be right here. This tau 1 is given by this equation. Tau 2 is given by this equation. These are the two same differential equations you saw in the Newton-Lagrange, or rather Newton-Euler formulation. So this chapter 3 of the Fu's book gives you two different derivations of the same robot. And they're both same value. So this is one thing I wanted to indicate to you. Now, the toolbox that Brad will describe This is release number 6, which is an old one. Now it's what, 9.9? You need to have the manual for 9.9. So download it from the website. And it actually gives you a set of commands. Chapter 2 is a tutorial for kinematic and then inverse kinematic. Here is the DH parameters that you saw and all DH matrix. And in it someplace you should have table of contents here. Okay. Now this is an old version. And homogeneous transformation group, quaternion group, which will discuss about interpolation and the polynomial and so forth. Kinematic group, inverse kinematic and forward kinematic, for example, and Jacobian methods, which we'll discuss later, and the dynamic. Remember Coriolis function? You have a command, friction, gravity load, and acceleration, okay, and so forth. So all of those, and then you have different models for robots. You have a dynamic model for one-linked robot. So you can actually, come to think of it, you can use the robotic toolbox to also do your homework number 1 by building one-linked robot. You can build your own robot in that toolbox. One-linked robot is a typical pendulum, but it's not necessarily inverted, it's pendulum. You know, you can, pendulum of the clock goes back and forth, that's the one we're talking about. Puma 560, that's a manipulative model for that. And this one is a Puma 560 with the modified DH parameter, which I don't want you to really bother with. I don't want to confuse you with the notation, with that. Even the author says a student get confused. Okay. Robot construct a robot object. This is general. Here is a Stanford. You have a Stanford arm in it. Okay. And the tooling robot, which is the simplest one, you can ask anybody. These are the trajectory generation. Cartesian trajectory, joint space trajectory, interpolated homogeneous transform. When you do a trajectory generation from point A to B, let's say you may even have 2 waypoints, you can have a command here to give you the transformation method for point A, waypoint 1, waypoint 2, and point B. You can find out how the H metric looks like at that point. And the way to check the accuracy of that H matrix, you check the 4th column. It has to correspond to the position of the robot at that point, which should be given to you. Okay, that's the idea. You have graphics, the animation plot and derived bot. Yeah. Derived graphic robot. Derived bot here is for mobile robot, which we'll see later. When we first started with this course here, about 5-6 years ago, the toolbox was only for manipulated robot. I was one of those who informed Professor Kork, said, why don't you put mobile robot? Mobile robot becoming much more popular these days than manipulated robot. And he delivered. So, for example, ACCEL is a compute manipulated forward dynamics. Remember that equation I showed you, Q double dot is D times one vector Q dot and Coriolis and gravity? That's for this acceleration. Q double dot is computed from that. And so forth and so on. So I'm not going to dwell too much because Berat is going to cover that. So let me now take you to a more detailed presentation of a fuzzy set. As you know, this course is loaded with new concepts, and one of them is intelligent control. There is a course, intelligent control, some of you are taking or have taken that. So this portion of this course is going to be enhance your other course. Okay. And this book is called Z-J book. One of my colleagues in Florida, and I wrote the book, and it's a combination of 18 or so chapters. Each chapter, there are several divisions are made there. In fact, if you want to download the entire book, you can go to this website also. You can go to this website, account.org/free publications by Mojamshidi. You can go and download your heart desire. Download free of charge. These are 11 of my textbooks. Okay? And that's my younger brother. So here is a linear system book that some of you have used it in the linear system course. This is a second edition of my book on large-scale system, published in '97. You can download that. This is the book I just was trying to tell you. Professor Zilucian and myself in intelligent control system using soft computing methodology. This is a book, Fuzzy Logic and Control, Software and Hardware Applications. You can download that, written by my former colleague, Professor Ross, and my former student, Dr. Wahi. Fuzzy Logic and Control, Hardware and Software Applications. This was an amazing book. I was teaching Fuzzy Logic course in New Mexico. And the whole book, the whole course was project, like here. We had groups of students like you sitting here. We divide them into different groups, and each of them created a chapter for that book. And it was published in New York, and with my students, undergraduates and graduates, mostly undergraduates, authoring that book. And I got a phone call from Motorola in Austin in 1990s, 94, 95, that we are trying to, we have got a fuzzy chip for Motorola. They announced fuzzy chip and fuzzy software. They wanted to have a reading material to promote, to go with their chips. They used this book. Not because of me, because of my students. Because they all, every chapter in this book, except the first 6 chapters, are practical. So download this. If you want to have some insight into your project, this book is very useful. Chapter 7 to chapter 18 are written by students. You know, one of the students here, Xavier, last semester was doing a laser pointing control. There's a chapter on fuzzy control of a laser, beam tracking. There's a chapter on manufacturing raising process. Chapter on traffic control using fuzzy logic. All kinds of things on it. So this book, it was really, and the publisher is the most successful book probably I have been involved with. 7,000 copies or so. Okay. This book was completed Aided Analysis and Design of Linear Control System, which is basically similar to this book. And this book is my 83 book on large-scale systems, modeling and control. So you may say, what is large-scale system? Large-scale system is a system where it's so complicated, what you have learned so far in your college year is not going to work. That's large-scale system. An example, the grid of the United States, electric grid of the United States. It's so interactive, so non-linear, so much involved, it's very difficult to handle it with typical textbook methodology. It was part of my actual PhD work way back at the University of Illinois. Now, the book is now in French because I was in France for 1 year and my colleagues in France translated it into French. Here it is, Système de Grande Dimension. So, it's a French, actually the cover is different, but that's a mistake that Patrick made. Okay. This is a book on time delay system, where you have delays in the system. And then these books are still on sale. I cannot give it to you like that. I cannot download it. However, I have pre-publication copy, which is not copyrighted yet. I can give you that. Now, this gentleman was interviewing today, looked at this book, and said, oh my God, I've seen this book. I said, where? It's at MIT library. And that's where he found it. So this book is also in Mandarin. Nobody here is in Chinese in this room. But, oh, you? No. He doesn't want to admit it. No, I'm just kidding. But this is in Mandarin. Okay, so they translated it into Mandarin in China. And these 4 books are actually available on Amazon, but don't go there. It's $185. So this is one way you can download. So for your book, for your specific need, these 2 books are useful. This one gives you some insight into fuzzy logic, neural network, genetic algorithm, and all that tools for intelligent control. And this is good for your projects. Okay. And so much for this. Now let me look at this. So we know that because of the fact that artificial intelligence and let me see, I can actually enlarge this. Because of the fact that AI have found their way into machines since 1980s. The first fuzzy chip was invented in 1989 by 4 Japanese separately. 2 were Japanese American, 2 were Japanese. Okay, and some of them actually, unfortunately, passed away. But putting artificial intelligence inside a machine, now you have a concept that Professor Zadeh coined called MIQ, Machine Intelligence Quotient. You know, you have heard of IQ. This is MIQ. Okay, so the question will be in the future that you want to purchase something. Let's say you want to purchase a video camera. Okay, next time you go to purchase a video camera, take a look at the specification of that camera before you decide to buy it, and see what features it has. There is a possibility that somewhere in that specification says this video camera has what's called the not vibration controls, but
motion stability. Motion stabilizer?
It's a motion stabilization, but it has a terminology which they marketed because the word fuzzy doesn't sound good in English language. And in English-speaking countries, like here, like Britain, like Australia, and so forth. No, New Zealand, I've lectured fuzzy in New Zealand, but they don't care. They have 32 million, 35 million sheep and 3 million people. They have a world of their own. Beautiful place. And if you want to go to one country before you are done, go to New Zealand. And that's one of our former students, Brandy, is there. Okay, so MIQ is a registered and patented concept which can now be attached to every machine that you find. So if it says motion stabilization when you buy the video, it means fuzzy logic is in it. So why is it big deal? Here, let's say you are taking a video camera. Let's say this is the video camera. And I'm taking a video of a bicycle running in front of my camera. Okay? And I can hold it and go like this, and it will be fine. It shows the whole thing. But sometimes maybe you have the bicycle standing still, and you take it in, and it still shows it moving because your hand is shaking. So fuzzy logic compensated for your hand being shaken, and it will show the image very stable. I used to have videos from this kind of experience using in the streets of Tokyo, and the person with the camera was sitting in a car, following another car, and taking video of the other car. So both the camera was in a moving environment, so was the target. And still the video looks very reasonable to your naked eye. So MIQ is going to be a future item on consumer product tables in the consumer product magazine in the future. Classical set, you have 0 and 1. We know that. Black and white. Okay, black and white. And pictorially, you have, let's say, temperature. This is a classical set of looking at the hot temperature. If the temperature is 40 or larger, let's say, Celsius, it's hot. And the membership value is 1. If it's below that, it's going to be not hot. Not necessarily cold, but it's not hot. Okay? But let's say you do the same thing as we said in our slideshow earlier in the course. Let's say you talk about the tall person. A tall person is one which is, let's say, above 6 feet. Some of you are tall in this room. Okay? 6 and higher. Okay? Now, if you are 5 foot 11 inches and 15 divided by 16th inch, you're just 1/16 of an inch shorter than 6 feet. You're short. You're not tall. Okay? So, I used to say, for example, in the 80s or 90s, President Clinton is about 6'2". Shaquille O'Neal is 7'2". Both of them are tall according to that definition. But put both of them on a basketball court to see who kills who. Okay? So that is the point. The point of the matter here is that classical representation, classical logic is not the best mathematical tool to represent a fuzzy set, a set which is ambiguous. Which means, when I say tall, it means different things to different people. If you go to Far East, I'm 5'9", I used to be 5'10", I shrank. Okay? I'm a still tall person if I go to Japan and I go to Korea. Okay? That's the point. But if you come to America, you're pretty short. Because a lot of people are above 6 feet. Okay? So, it's all a matter of degree. That's behind fuzzy set. Everything is matter of fuzzy set. I have been recently invited to give a short talk about the life and the contribution of Professor Zadeh to an international audience. And I've been reading his biography. Let me just finish the lecture by this. It's a very unique historical point which nobody knows except he knows, describing his own biography. His parents, he lived in Berkeley from 1958 onward to now. He's now 95 years old. And his parents lived in New York City. All of them immigrated from Iran to New York. And he went to see his parents. His parents were out of the apartment. He was home alone in the apartment. And he was looking at the timing of visit, timing of rendezvous with some friends. They were not on time. It came to him that things are so approximate. Why are the people are not coming there in punctual like the Germans and the Swiss, who are very, very punctual? The concept of fuzzy set came to his mind at that point, visiting his parents in New York City. And then he wrote a paper which nobody wanted to publish it. They said this is voodoo science, voodoo engineering. Professor Kalman used to say that, of the Kalman filter, whom I also know personally, a very good mentor of mine. So, Zadeh proved Kalman wrong in the sense that right now, if you go to World Patent Index, there are probably 50,000 patents on fuzzy logic devices. No. You have fuzzy logic in elevators, in transmission of your car, in almost anything you can think of, it's been there. Okay? And of course, he received a tremendous amount of awards for what he did. So he is the father of fuzzy logic. Is what I coined for him in 1992. Like Ed, bless his heart and bless his soul, Joe Engelberger, father of robotics. So you are taking robotics course and you're also taking some history course, because I love history of science and I like to share that with you. See you next time.